have sort of three phases to my talk. We'll use phases. We always talk about phases at NASA instead of parts, right? It sounds more important. So there'll be three phases in my talk today. The first phase will be a little bit of project management science 101. So a lot of you here in the room build hardware and manage the projects to build hardware, either systems for vehicles or components for vehicles, or those of you at Goddard may be instruments or satellite buses to house instruments, all of those pieces. And I want to talk about, kind of from a project management perspective, what's different when the hardware that you're building is also supposed to be a working laboratory, because that's something we haven't done very often at NASA, and that makes ISS a little bit unique. The next thing I'm going to do is talk about the 5 most important results from the early utilization assembly period. And there will be a quiz after that. I'll give you a little bit of details when we get to that part. So you'll have to pay attention. You'll have to take a couple of notes. And it's just how it's going to be. And then, and then the third thing I'll talk about is I'm going to talk about the upcoming plans for one specific experiment on ISS. We have about 120 experiments active in any 6-month period now. And so I'm only going to pick one of those, and I think you'll see why I pick the one I pick when I get there. Just be thankful I'm not having a quiz on all 120 experiments at the end. So first of all, sort of ISS Laboratory 101. This is a development process that we all know and love here at NASA. And from the space station's point of view, there's a design phase, and that, in the case of the space station, was decades, including the Freedom design and all of the redesigns after that. Then you have the assembly period, which has really been the last 11 years or so, where from the very first module going into orbit until the last module going into orbit and we declaring assembly complete. Our Russian colleagues, by the way, have not declared assembly complete. They still have modules they plan to launch. And here we are today in 2011, and we're really only halfway through the project from a research perspective, because what comes next is the utilization phase, where instead of your goal being building it, your goal is using it. And of course, utilization is a horrible word. All the tech writers say you should never use that, but that's the word that we're kind of stuck with. And then, if you do your job well in this phase, then you extend the life of the mission. The Voyager life is long past the design life, what it was originally planned for, but it continues to collect data. And if we do our job well at NASA, and we get the accomplishments and the research accomplishments that are the promise of the hardware that we build, that extension should also be part of our mission, because that means what we've done has been so important, it's worth continuing to do beyond the nominal timeline. So what does this mean? So this is kind of the project management viewpoint at a very macro scale. Well, so what happens on the science side in parallel with this? On the science side, that early stage is the stage of promises, because the scientists are trying to communicate why they want that laboratory. And depending on how long the design phase goes, the promise phase can be really politically challenging, because you can make some pretty big promises for a couple of years. But if you get into major redesigns, then people start circling back on whether or not those promises are worthwhile. And so there's a lot of political challenges to that early phase. And of course, scientists are projecting what they think might happen, but nobody really knows. And so there's a lot of opportunity for scientists to criticize each other and have disagreements, and that can introduce political problems. Then, even more challenging than the promises phase is the waiting phase. Everybody knows what we thought we could accomplish, and then we spend 11 years not really doing it while the vehicle itself is assembled. And there winds up being a huge amount of replanning and restructuring of the scientific program in that time period as the vehicle itself hits budget challenges, schedule challenges, and that really has a huge impact on where the science is once you get to this point in time. So now here we are, we're beginning our full research phase, where the research mission of using this as a laboratory is secondary only to operating the vehicle safely. And then, of course, the benefits from early in this phase, as they emerge, become the justification for the extension and determine what you do during that time extension. And then finally, I wanted to put up a flow in terms of organizational culture, because this is also really important. So in this early stage, you do a lot of requirements and planning. And those of you who have been working in various aspects of the Constellation program have just spent the last 5 years of your life, for example, working this phase over and over. And that introduces one kind of a culture where you're defining requirements, ridding requirements, reviewing them, trying to get them very specific. It's a very engineering and system-centric kind of process. Then when you get to assembly, it's all about the vehicle and the crew, because everything you do, you're doing for the first time out of that plan. You're very worried about the risks of losing everything, about having solar arrays don't unfold, or ports don't open, all of the things that can go wrong when you're doing a one-off mission to assemble a complex vehicle. Then, as you get to this transition, suddenly you need to have a research mission focus. And right now in the space station program, we're really struggling with that cultural change, because for the last 11 years, if a systems manager made sure that their system functioned 100%, they never got yelled at and they were doing their job perfectly. But in order to manage those systems at 100%, those systems managers were a little bit unconstrained in terms of how much resource they could use, how much crew time, how much upmass, how much resupply. As long as the vehicle was being assembled correctly, that was enough. Now today, that's not enough anymore. Now the vehicle has to perform something more than just operating safely. And so that's a real challenge to us, and I'll talk about that a little more. And then of course, the research mission renewal is that final extension there. And so in order to have all the work that we did early in terms of all the designs, the redesigns, the assembly, in order to have that really pay off for the American public, we need to get all the benefits out this back end. And that requires us at NASA to make some pretty big changes, both in the way that we approach operating the vehicle and in the way we approach management of all the different projects that are included. So a couple of paradigm shifts which I've mentioned. One, that operating safely is not enough once you switch to that research mission, because if you operate perfectly safely but don't get any of the research done, the vehicle will be deorbited rapidly, because the mission now is the research mission. A second point that I haven't made yet is that experienced systems managers that are used to managing Crit-1 systems can become very judgmental, and operations teams as well, they can become very judgmental of researchers. Right? Because for the vehicle, if you're in charge of the ECLIS system, you want that to have 95% availability, and you don't want things to break, and you want all your supply chain to be perfect. And the crew's life and health are at stake if you fail horribly in that. So we get used to an operations culture and a systems management culture that doesn't allow mistakes. And yet research in a laboratory setting requires mistakes. You've got to be trying something new every time. The hardware for the system on ISS is pretty much done now, and we're going to use that same hardware for the next decade. But we're developing new research hardware and trying new things on the research side every day, new procedures every day, checking out things every day. And I see sometimes challenges in the cultural response of the mission control and the systems professionals when they look over at the research side and say, well, you know, they sure didn't develop that very well. Didn't they think of this, that, and the other? But in a research environment, it's okay. In fact, because the ISS is a real laboratory, we expect that to be the case. And the whole point of having a laboratory in space for decades was so that scientists could make incremental improvements, rerun things, try things in different ways. And so the reason science made the advances that of course, science made the advances it could during the shuttle era. But if you look at it from the point of view of a biologist, say, a biologist might fly on a space lab mission and maybe their experiment was only half successful because some things didn't go as expected. And they would have spent 2-3 years designing and perfecting their 8 hours of joy on that 2-week shuttle flight. And then their next flight opportunity would be 5 years away. So you can't make scientific advances on that kind of a scale. On the space station we can, because you can try something every month. If we have an experiment that fails, we can change out parts and do something different and get it fixed within a couple of months. But there are definitely cultural aspects to that different approach. So just to give you kind of an overview of the objectives for research on the ISS, when the ISS was designed, everyone expected that there would sort of be a mother organization that would be the NSF of space, and it would define and do everything on the ISS. And the way that we are today, having survived the waiting process and the promises process, is nothing like that. It's completely different. So the way that we are today is, of course, we have the partnership, which is a large portion of the research on ISS. So this circle back here represents the Russian pie, and this little wedge right here represents the part of the pie that our partners have earned by the investments that they've made in developing the laboratory and the vehicle. And then the rest of this represents the rest of the US OS pie, which are the US resources from the US operating segment for research. And we have two major flavors of that research. The first is the NASA-funded research, and by Congress, starting with the NASA Authorization Act of 2005 and echoed in 2010. That is defined as focused on NASA's exploration mission, which means we see things like the Human Research Program, looking at how to improve astronaut health so that astronauts can safely explore beyond Earth orbit. Life and physical sciences specified by Congress at a very low level so we don't lose that capacity within the US scientific community. Technology development and demonstration, so that's the work, much of that work had been in ESMD and is also transitioning to the Office of the Chief Technologist today. And then astrophysics, heliophysics, Earth and space science, the work, the exploration mission of the Science Mission Directorate. So all of those are in the NASA-funded research side. But that's really a fraction of the kinds of things that Space Station was designed to study on orbit. And so what Congress has told us is they designated ISS as a national laboratory. Now, it turns out there's no legal definition of a national laboratory other than everyone kind of recognizes it means one agency operates a laboratory and other agencies can access that, whether that be Brookhaven National Laboratory, Savannah River National Laboratory, and so forth. And there are three kinds of users that come in and are interested in using ISS for their own purposes, not related to NASA's exploration mission. And those users are the commercial sector, and when I start talking about results, you'll see why the commercial sector might be interested in ISS. Nonprofit organizations and US government agencies. We have agreements with, of course, the Department of Defense, also the Department of Energy, the National Science Foundation, the National Institutes of Health, and the US Department of Agriculture all have interests in using this laboratory. And some of you probably know, oh, I should mention this light blue area around the outside just points out that education is sort of almost a frosting on top of the pie. If that makes any sense? I don't know, frosting on pie. It surrounds all the work that we do. So the NASA-funded research often includes significant education components. The international research has significant education components, and the National Laboratory itself has a number of goals in education. And so it kind of perfuses all the work that we do. So the infrastructure was adding the infrastructure to ISS, the bones of the research laboratory, if you will. These are our lab benches and our desktop equipment in our lab, and all of that was part of the assembly process as well. And as those rack facilities went on orbit, that allowed us to get a little bit of research started in the nooks and crannies of crew time between assembly missions. So when I talk about early utilization results, I'm going to talk about the results of the things that were done in the corners of the assembly mission, and as these facilities came online and were brought up in the assembly process. What's great about this is we now have the infrastructure in place, and we have a modular infrastructure, so if there's a new piece of hardware that nobody thought of before that we want today, it can be built relatively inexpensively and plug into one of these standard rack interfaces. And ESA and JAXA as well have their infrastructure, and we have great mechanisms in place for sharing hardware if they want to use one of ours or we want to use one of theirs. So in project management lingo, let's set budget aside for a moment, there are three primary resource dimensions that determine the throughput of the laboratory, and they are interrelated and correlated in some ways. And those are up mass, crew time, and down mass. And so depending on the vehicle you fly, up mass and down mass are correlated. If you take your up mass up on a SpaceX Dragon, you get pressurized and unpressurized up mass, and you get return because the entire pressurized capsule of Dragon comes home every time. If you put your up mass up all on orbital, you don't have much down mass return because the orbital vehicle doesn't return anything. So you get trades between up mass and down mass, and then you also get trades between up mass, down mass, and crew time. So the main thing that, of course, determines how much crew time you have is how many astronauts you have on orbit. The second thing that determines it is how much time they have to spend keeping themselves alive and breathing and keeping the vehicle operating safely. And the challenges of crew time are that the other big overhead that you have is how much time they have to spend loading and unloading visiting vehicles. So under a shuttle paradigm, you have 6 or 7 astronauts that launch with the cargo and can help during that peak unloading period of putting everything in the garage, as our previous speaker said. Now, under the new paradigm, post-shuttle, you have a larger number of small vehicles and no crew coming with them to do the loading and unloading. So we see impacts of that substantial programmatic change on the crew time on orbit. I had said we would set cost aside, so I want to come back to that for a minute, because the cost side of the research equation doesn't rest within the ISS program. That's one thing kind of unique to this compared to any other national laboratory. Most other national laboratories have about 80% of their funding for the research from the core agency. And NASA does not have a budget line to fund 80% of the capacity of the use of the ISS. And so we have a classic supply-demand curve where things that decrease the amount of research on ISS are resource limitations, flight delays, ops scenarios that affect crew time for research. Also, the cost to use the platform, both the transportation costs and the cost of payload development itself. So all of those things reduce demand for the laboratory, and we try to work on all of those to remove those pressures so that they don't constrain our users of the laboratory. And then you have research demand, which can be driven by NASA funding. If you add more funding to NASA, you'll increase research demand by funding more researchers to do the work. Non-NASA funding, whether that's from the private sector or the public sector. And research breakthroughs themselves generate interest in the laboratory. And those are probably the most important as we look out in the long time frame. Because right now, a lot of people are willing to take a try at it. But the sustained users of the ISS will be those that find they get a valuable return on the investment they make in using it today and want to continue using it over the next decade. So here we are just from a crew time perspective. It's useful to see this is a cumulative graph of the crew time for research through 2020. This is, our target is 70 hours a week across the vehicle, so about 1/3 of the crew time being spent on research. And if you look at that cumulatively, here we are in 2011, we've really hardly begun. We're really just getting started. So when we look at the ISS program as a whole, Americans have reaped two major benefits already. Those benefits are the benefits from really design and development of an engineering marvel. Everything we know at NASA has been turned on its head by the work that we did in building the space station. We now know more about how to operate a long-term platform than we ever knew from, say, our Skylab experience. And so the engineering achievement itself has already made major paybacks to the American people. And then we've also gotten some real paybacks from peaceful international partnerships, and you've heard that a little bit in several of the presentations already this week. But the research accomplishments of the next 5 years are going to be the thing that determines the lifespan of the space station. So all of these things were good reasons for building it, but they're not good reasons for continuing to operate it. Now it comes down to that research mission to determine how long it's valuable to operate the platform. So I want to briefly mention the kinds of benefits that come from research in space, because there are three kinds of those. And if you get them mixed up, sometimes you can get yourself in trouble, both in the political arena and also in the scientific arena. One thing you can do on ISS is you can make discoveries, because on the space station, we can do research without gravity, with the gravity factor removed. And that amounts to a whole series of experiments that essentially can't be done on Earth. In a drop tower or parabolic aircraft, you can get seconds of gravity being taken away, followed by a real significant multi-gravity thunk, whether you do that in parabolic aircraft or not. So if you want to do anything over a long period of time, anything that's not an instantaneous effect, that experiment has to be done in space, in a microgravity environment. And in fact, if you think about it from that perspective, we scientists say to learn something, you've got to control every factor. And gravity is the one factor that almost every experiment we've ever done, all 20 million scientists that have done experiments, say, throughout human history, most scientists have never done that ultimate experiment of controlling gravity in whatever they were studying. Another area, or another reason we do research in space is for the Earth benefits. If there are discoveries that we can make that turn into products or services or materials or things that make human life better and also make commercial sense, then those kinds of benefits are important. And then the final reason, of course, we use ISS is the one that resonates the most to us within the agency itself, are for space exploration purposes, to use it as a test bed to help us extend our reach beyond Earth orbit, to know how to transit astronauts to Mars safely and have them able to take care of themselves when they land and so forth. And so this focus of NASA's mission, I'm not going to talk any more about today. You heard a little bit about it, and you got a good flavor of that in Scott Smith's talk yesterday, because he's very focused, even though there are some Earth benefits that cross over, and you see these all overlap, but his work is very much focused in the Human Research Program, focused on exploration. You've also heard some discussion of MIR, some discussions of technology tests on ISS. Some of you know that STORM is launching on the shuttle next week. A classic example of proving a technology on the ISS. That's an improvement in docking technology for Orion purposes. And so we continue to do that work as well. What I'm going to focus on in the next part of my speech, oh my goodness, that went fast, is Earth benefits. And so I just got the signal I had about 5 minutes, so pick up your pencils. And here's what your assignment is. I'm going to talk about the 5 most important early results of the space station. And your assignment is that of those 5, you need to pick one. And when you get back home, you need to tell one NASA colleague about it. You need to tell your spouse or significant other or someone in your family about it. And you need to tell a neighbor about it. Because if at NASA we don't understand the important goals and the important accomplishments of each of our programs, we're failing each other as a community, and we're failing our agency. So, we all need to be able to say why Hubble matters. We all need to be able to say why the James Webb Space Telescope is important. We all need to say why exploring beyond Earth orbit is important, and we need to know a few of these things. So, buckle your seatbelts. I'm going to talk about 5 results, 3 of them in biotechnology, bacterial virulence and candidate vaccines, Duchenne's muscular dystrophy, and water purification technologies. I'm going to talk about a drug for treating testicular cancer and fundamental equations for capillary flow. So here we go. One of the first discoveries we've made through the ISS era, and partly on shuttle flights to the ISS, is that bacteria respond to being in space in one of 3 ways. They either get more virulent, so these guys are colored red because they're bad guys, or they reproduce more rapidly, which also can make them more able to cause disease, or nothing affects them at all. And most importantly, using modern genetic techniques, when we see these changes in space, we can find out what part of the bacterial genome is being expressed, what part is activated when they're in space to introduce those changes. So what happened with the first bacterial research in space is that scientists found when they flew salmonella, that's the salmonella that causes food poisoning, to ISS, it became more virulent. So each individual microbe became more able to cause disease. And most importantly, they determined which genes turned on to cause that impact. That led to a series of 2 competing teams. We actually had that original team fracture. Scientists started looking across a variety of species of bacteria to find out if this is true in all bacteria or some bacteria. Are they the same genes? Are they different genes? And so now we have, under the national laboratory side, commercial development of tests for vaccines going on actively. So AstraZeneca is has flown about 14 flights now, where they're looking at could they use this as a shortcut to vaccine development and identify bugs that don't make you sick but do make you immune for the future. And they've extended beyond salmonella now to methicillin-resistant Staph aureus, which is the superbug that's antibiotic resistant that really kills most of our grandparents. In the end, you're most likely, if you don't die of cancer, you're most likely to die of a MRSA infection in the hospital as you age. At the same time, NASA funded work, because we were interested in this from an astronaut health perspective as well, led to studies of other microbes, Pseudomonas, which is the bacterium that caused a UTI infection in one of the Apollo 13 astronauts, as well as something that causes infection in a lot of burn victims. So Pseudomonas has now been studied, various staphs and various strep infections have been studied. And so we're starting to get a sense. There's a little mini gold rush of microbial biologists using the space station now, trying to understand how to use this to help us win the war against microbes. And that's a big war, and it's a war that we're losing. So it's a really important application. And this just gives you some pictures of the nasty creepies that are being tested on ISS. The next example comes from the Japanese work. At NASA, we canceled our protein crystal growth studies about 5 years ago. But our Japanese colleagues did not. And this is a molecule for a protein called human prostaglandin D2 synthase inhibitor protein. You don't have to write that down. The crystal that the Japanese scientists built on ISS is only slightly better than the best crystal that was made on the ground. But what it allowed them to do was image this water molecule right here, which suddenly explained why the protein folded the way it did, which gave scientists enough insight to develop a candidate treatment for Duchenne's muscular dystrophy. Duchenne's muscular dystrophy is a genetically triggered form of muscular dystrophy. It affects about 1 in 5,000 men, young boys, and they are completely debilitated by the time they're 9 years old. So it's a very tragic disease. And this has now proceeded to a phase of clinical trials in animals. And one of my Japanese colleagues showed some really compelling video this summer from their first trials in animals where they had related sibling dogs, and the puppies, one was given the drug treatment and one was not, and they had this genetic problem. And after about 6 months, one of the dogs could barely walk, and the other dog looked completely normal, was able to run in a completely normal way. One more biotech area in cancer treatment delivery. These are microcapsules. Think of them as little balloons that can be constructed from lipids and contain a small amount of a drug. This was very early in ISS. We flew an experiment to build the microcapsules because scientists thought they could use microgravity to build capsules that would have properties that would help them treat the testes so that they would be attracted to testicular tissue and that could be used to deliver a treatment for testicular cancer. And obviously testicular cancer is a real problem in this country, and it's a problem it has a high incidence and it has a very high fatality rate. What the scientists did, they proved on ISS they could make these. They then had to sharpen their pencils and spend 5 years on the ground to develop a piece of hardware that could make these in clinical quantities. Because we certainly didn't want to be trying to produce these on ISS and get them back and forth. That would not have been a very effective approach. So after 5 years, about a year ago, they patented the piece of equipment that can make these on the ground, and they're now doing the fundraising to start clinical trials in human studies at MD Anderson Cancer Center. Okay, so I just gave you 3 really exciting, compelling kinds of possible things that could cure disease in humans, and they're really exciting. The challenge for us is that it takes 5 to 30 years for a scientific result like that to make it into the clinical marketplace where your doctor can give it to you if you need it. And we call this the Valley of Death. So here you see a research scientist over here with some test tubes, and here you see a doctor with a sick patient, and down here you see all of the great ideas that don't make it across that valley. And this is an area of really active work in the National Institutes of Health. It's not unique to NASA. It's true across all biotechnology research. And so it's hard to know for sure whether these kinds of compelling results will make it into a treatment in the end. There are so many things that can go wrong along the way, including just a pharmaceutical company deciding the market isn't big enough, or there can be a side effect that was unintended. All kinds of problems can happen. So I don't want to oversell these kinds of results, but that said, if you can get results of this nature that are this compelling, it's pretty easy to say that over the lifetime of ISS, something is going to be a significant breakthrough. And that's the important take-home message. Just 2 other quick examples. From our RegenEclus development, of course, what we need in space is we need things to be small and low power and not use too much resources. And part of the water system development included a bed reactor that turns out to be really useful for deploying in disaster areas. So this is that same technology deployed in Pakistan after the earthquake a couple years ago. It doesn't require any power at all in this configuration. All you need is a gravity feed. So if you have some hills, you can connect it and provide a water supply for an entire village, and it's very low maintenance as well. And finally, in the area of fluid flow, some applied research that we have going on really aimed at making fuel tanks lighter. And you heard Howard Ross talk about some of the shuttle work in this area. So capillary flow is your old reliable for moving fluids in space. Because once you don't have gravity holding liquids in the bottom of a container, capillary flow can become dominant, and because it isn't affected by gravity levels, it can get you where you need to be. And so from a series of experiments called the capillary flow experiment on ISS, scientists at Portland State University have developed the first set of fundamental non-analytical equations for capillary flow, which they're now using to model a variety of container sizes, and they're using to look at how many veins do you really need in a fuel tank. Can you reduce that to reduce weight and mass? So it's very useful to NASA, but it also allows you to do things like design super sponges, super wicks, other things that will move fluids rapidly on the ground. And there are 3 patents filed. So that's the end of the part where you got to pick one of those. And at the end, I'll have some links if you want to go back and review material, and the charts will also be posted online if you want to take a look at those. Make sure you've got your elevator speech ready. And I want to close by talking about just one experiment in our future, and this is an experiment in the absolute purest discovery mode there is, and that's in the area of fundamental physics. So we have all these disciplines that use the laboratory because they're studying microgravity. And then we have some disciplines that use the laboratory for the same reason people climb Mount Everest, because it's there. So once you have a laboratory in space, you have the most amazing power system ever in orbit. And the alpha magnetic spectrometer is going to the ISS next week, hopefully, for no other reason than to sit on and be a parasite on our solar arrays and collect the most detailed data ever on cosmic rays. And so I want to talk about that science a little bit. Its mission is to advance knowledge of the universe by helping us understand antimatter and dark matter by measuring cosmic rays. And here's an artist simulation of it mounted outside in the ISS truss. It's, the lead investigator is Dr. Sam Ting, who's a Nobel laureate from MIT. It's primarily funded partly by the Department of Energy and also primarily by an international team, not funded really by NASA, other than the flight support of launching the instrument. So what's the AMS going to do? And I know you, like me, are really comfortable bringing up antimatter in cocktail conversations. So let me try to give you a couple of hooks, because this is a really important instrument. It's the most expensive instrument we'll ever put on the ISS. It's probably one of the more expensive instruments we'll ever fly in space. And understanding what it's going to accomplish is really important. So the 3 goals are antimatter, dark matter, and strangelets. So I'll give you the quick rundown. Of course, antimatter, the challenge with antimatter is you never observe it in space, because every time antimatter finds matter, they collide and produce nothing. In 1999, AMS-1 flew on the Space Shuttle, and they got the most sensitive measurement of the anti-helium-helium flux ratio. And this is a picture of what anti-helium looks like in a particle reactor. So if you use a particle breaker and you get an anti-helium nucleus for a very tiny fraction of a second, this is an image of what that looks like. So 10 to the minus 6 is the best sensitivity we've had so far. The holy grail is to actually see an anti-helium nucleus in space, because so far we've only seen them when we make them ourselves in the middle of a particle accelerator. And AMS-2 is going to increase that sensitivity from 10 to the minus 6 to 10 to the minus 9. So that's a huge improvement. I'll show you that in a graph just real quickly. Next is dark matter. In dark matter, the thing that you're searching for is neutralinos. And if they exist, they should give off this excess of charged particles. And so what AMS will do, and this is an artist's rendition of, if you, instead of lighting up all the matter in the universe, which is what we normally see when we look at images, say, from Hubble, this is an image of if you turned all the matter dark and lit up the dark matter instead of lighting up the matter. This is an image of what the universe might look like. And so by having this high sensitivity, it also allows to identify peaks in these kinds of fluxes that would be related to dark matter. And then finally, strangelets, once again, are something that we see in particle accelerators, but we don't see in nature coming in from the cosmos. So there have been 6 types of quarks identified when we do particle acceleration experiments, but only up and down quarks have been observed on Earth coming in from cosmic rays. And so the question is, why don't we see the other 4? And those other 4 are called strangelets. And so the theory says that the strangelets would have extremely large mass and very small charge to mass ratios. And those ratios are so small that there's never been an instrument that could detect that ratio difference. And this AMS is expected to be the first instrument to do that. So just to I'm going to skip those 2 and just kind of give you a sense of, this is all the data collected to date in these blue, green, and dark blue circles from AMS-1, HEAT, and Pamela. And this purple is the data that you expect to get from AMS. And you can see it pushes the graph way out, especially over this hypothetical curve. So it really should allow us to get some breakthroughs in whether or not these unified theories of fundamental physics are true by getting some real observations to support them. So that's why you can say, and of course Dr. Ting says this all the time, that AMS will give us a new fundamental understanding of how the universe works. And that's sort of the 3-minute version of why that might be. So let me stop on this chart right here and leave it up for just a second, because we're working really hard to communicate about all of these results. But one of the challenges is we're all in a sea of information overload. And so knowing how we're communicating and being able to tap into that is important. We have a blog called Aloft, and you can see the link there to the government blog site to get there. Once a week, we have a personal account from one of our researchers posted, or perhaps an observation from me every now and then you'll get stuck with. We also have a Twitter account that tweets about 1 to 3 times a day, talking about what's going on Space Station, what's being published, and so forth. And on the World Wide Web, you can just go to this very short link on nasa.gov. We post 2 to 3 stories a week as well about research on ISS. And we're getting, a large number of stories out there in the media, but the media market itself is so fractured that it's really hard for people to stay informed about all the diversity of things going on. So definitely hone in on some of these tools. Try to keep informed about what's going on Space Station, because the next decade is really going to be exciting. Thank you.